All right, section 6.4, the central limit theorem. All right, this is going to tell us how we can use some of our normal distribution properties for samples of normally distributed items. So let's take a look. So we're going to look at how it's going to be important in applications. Well, I just said that. Central limit theorem. Let's take a look at what we need. We need to have sample sizes, not population sizes, but sample sizes of greater than 30. Sampling size, the sampling distribution of X bar, in other words, of the means, can be approximated by a normal distribution with a mean of mu and a standard deviation of sigma over square root of n. That means if we're getting a lot of means, then we can talk about those means being distributed, as we talked about in the last section. Okay. All right, when can we use the central limit theorem? Let's see, what do we have to do? We have to have a population that has a mean mu and a standard deviation sigma, and simple random samples, all of size n, are selected from the population. Now, they need to be random. They can't be specific. Right? Now, when we have this condition met, then the mean of all of our means, mu of x sub bar, is going to equal mu. The standard deviation of all values of x bar, sigma sub x bar, is going to equal sigma divided by the square root of n. And to do a z-score conversion, we have x equals, for x bar, we have z is equal to x bar minus mu over the quantity sigma over square root of n. All right. A lot of letters, a lot of bars, square roots, plenty of Greek stuff. This will be a little bit clearer when we get to an example, which is coming up soon. All right. When can't we use this? We can't use this if we have a population, or excuse me, if we have a sample that is less than or equal to 30. So it's not going to work in that case. All right. So always make sure to check to see if we are having a population above 30 first. And then check to see if we are looking at a single value of x. In other words, are we looking at a single experimental outcome, or are we looking at the outcome of an average of samples? If it's a single sample and we want to get a z-score, z is going to be what we've talked about before, x minus mu over sigma. If, on the other hand, we have a collection, then we'll have to use our other equation, which we had before here, x bar minus mu over sigma over square root of n. The sigma over square root of n needs to be divided first before you put that in the bottom of the fraction x minus mu. So be very careful about putting that in your calculators. All right. So this is just going over again. If we have if we have x bar here, mu of x bar will be mu, and the standard deviation sigma x bar will be sigma over square root of n. Now, sigma x bar is called the standard error of the mean, SEM. All right, an example. So hopefully this will clear up some things. All right, safe loading of elevators. The elevator in the car rental building at San Francisco International Airport has a placard stating the maximum capacity is 4,000 pounds, or about 27 passengers. This converts to a mean passenger weight of 148 pounds when the elevator is full. We will assume a worst-case scenario in which the elevator is filled with 27 adult males. Assume that adult males have a weight that is normally distributed with a mean of 189 pounds and a standard deviation of 139. Find the probability that one randomly selected adult male will have a weight greater than 148. Alright, so we have a mean, mu is equal to 189 pounds, and sigma, our standard deviation, is 39 pounds. Alright, so we want to keep that information there. So, A, find the probability that one randomly selected adult male will have a weight. So let's write down what we have. The mean weight of a man is 189 pounds. Sigma is 39. And we want to figure out what our z-score is. Now this was for an individual person. So our z-score will simply be x 148 minus mu 189 divided 189 divided by 39. That will get us 148 minus 189 divided by 39, negative 1.05. Now, we can put that into a z-score. That will be negative 1.05. And this is what we dealt with last time. Equal normal dot standard dot distribution. And so that'll give us 14%. We want to know the chances of it being above that. So that'll be 1 minus that distribution. So 85% chance that an individual man will be above that weight. Now that was negative 1.05, so we got negative 1.05, 1469, and subtract that from 1. So that would be 1 minus 0.1469, and that gives us 85.31 using the z-table. Okay, don't know what that is. Alright, so B, find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148 pounds. So now we have a sample, 27. So, we got a problem with that. And the problem with that is now we have a sample of 27. And we're supposed to have at least 30. So we should have over 27. But we're going to go ahead and look at it anyway. So this is the example with a negative 1.05 where we had just an individual. And we end up getting 89% chance for that. Alright, so we can use the normal distribution if the original population is normally distributed or n greater than 30. But we can make an exception if the sample size is not greater than 30, but the original population of weights of males has a normal distribution. So as long as they are distributed normally, we can still use this. Don't recall reading that, but let's go with it. Especially since it's our only example so far. Alright, so now we are dealing with a sample of 27. X of mu equals 189. Got that. Sigma x bar equals sigma over n, which is 39 over square root of 27 gives us 7.51. Now, if we graph it here, we notice, well, that's a lot different. It looks like suddenly we have almost any chance of getting this. So we again plug it into our z, and we get z is equal to x minus mu x bar over sigma x bar. And that gives us the number negative 5.46. So if we look at our table here, negative 5.46, it does not go that high. So what we will need to do is we will need to use Excel for this one. So this one, and again, negative 5.46, negative 5.46. Okay, that gives us 1. Well, that's not very helpful. So I'm going to expand this and see if it'll give me some more decimals. Here we go. 0.999999976. What I'm going to do is I'm going to take this and multiply it by 1 billion. 9. So that's 1 million, billion. So 23 in a billion chance that you will not be over that wavelength. So do not put 27 adult men in there. Maybe 27 children men, that would work. So we see they're definitely going to be over that amount. Right. So it'll be overweight if stuffed with 27 randomly selected men. If they're 27 hefty men, 27 wrestlers, 27 big people, probably not going to work either. All right, introduction to hypothesis testing. Now this gets interesting. So with hypothesis testing, what we're trying to figure out is we make a hypothesis and we test to determine if it can be falsified. Falsification is one of the things you don't hear about too often in science, but it's very important. Any hypothesis you have has to be falsifiable, otherwise it's not a scientific hypothesis. So that means if we take a sample, and our sample is significantly off of what we would expect it to be, then that our hypothesis most likely needs to be revised. And that's perfectly fine. Hypotheses are revised all the time. Once a hypothesis is tested often enough and it's shown to be correct often enough, it'll then transition into a theory in most cases. All right, body temperature. So, assume that human body temperature has a mean of 98.6 degrees Fahrenheit, 37 Celsius, 310 kelvins, as is commonly believed. Also assume the population standard deviation is 0.62 degrees Fahrenheit. This is based upon data from the University of Maryland. And let's say we had a sample size of 106. This is randomly selected. We find the probability of getting a mean of 98.2 degrees Fahrenheit or lower. So 106 is over 30, and we also assume that it was normally distributed, so we are good to go. All right. Mu sub x is equal to mu is 98.6. This was by assumption. This was our hypothesis. And sigma x bar is equal to sigma over square root of n, which is 106. We plug that into our calculators, we get 0.0602. All right. we can take our temperature, 98.2, subtract it from 98.6, and divide it by our sigma x bar, 0.06, and see what we would get for our z-score. So we can see that 98.2 is going to be pretty far down here, where this is 98.6. So very small, giving us a z of negative 6.64, which is lower than we had before. So this is off the chart. We could use Excel if we wanted to, but again, we'd get an exceedingly small number. And we can try that. And so, what did we have? 664. 0.64. So even out of a billion, 15 out of a trillion chance that would happen randomly. 15 out of a trillion is, well, that'd be less than 1 in the entire population of the Earth. So it is very unlikely that this was random. Right. So chances are practically 0. Something in a trillion. So when we looked at this, what we can do is either try to determine if our hypothesis was incorrect, 98.6, as being the body temperature of humans, or we could try to figure out if the population sample size was too small, 106. It seemed to be 30, so that's not too bad. How are these people chosen? If it was not random, that could be another issue. Was it a particularly cold day? That's a possibility as well. Was it an instrumentation problem? Right. So that's something else you could look at. If you're consistently getting the same numbers off by the same amount, it could be that you have badly calibrated thermometers. So there are a lot of different options. But if you're testing the hypothesis, you're most likely going to say the hypothesis has a chance of being wrong. Now, one of the things is if you compensate for everything else, this is going to be very detrimental to the hypothesis. And one of the things about hypotheses is that you can eventually prove them wrong. Proving them right is almost impossible, though. But once you have enough evidence, you can go with the assumption that it's right until something better comes along. All right, and lastly, what if we have a finite population? Now, this doesn't normally matter if we are dealing with a very small percentage to be in our sample. 10,000 people out of 300 million. But if we have a sample size that is greater than about 5% of the total population, we can adjust our sigma x bar by multiplying by this correction factor. Square root of big N minus little n over big N minus 1. All right, we just multiply that by our sigma, and that will give us a corrected standard deviation. All right, and that is it for the central limit theorem. Next up, accessing normality.